Let us now look at the bell curve, which is extremely important for us. And binomial Poisson you can read, but this is very important. So let me go give you the perspective. In the video you have binomial Poisson by me, but I feel this is the most critical, the pivotal point. So let's play safe and do some justice to that. The first question which I ask is, because it looks like a bell-shaped one, it's called a bell curve. And it can deal with fractions, it can deal with continuous variables, it can deal with 22.23 kg. What is the probability that it will meet the customer specification with this kg? It can do all that. And it is a distribution which has an outstanding property. Mean, median, mode, all are friendly with each other, they are equal. If I can say in a lighter vein, normal distribution is secular. All mean, median, mode, all are equal to one another. Mean is equal to median is equal to mode. So mean, median, mode, all the three are equal. It looks like a bell. Then the property of symmetry, empirical rule we said, it's symmetrical about the mean value, 1 standard deviation, 2 standard deviation, 3 standard deviation. Yesterday we did that. This is extremely important for knowledge, standard, specifications and all. There is another property. When I extend the tails of the distribution, it will run parallel to the horizontal axis without actually touching the x-axis or even cutting it. Even if you cry, nothing will happen. From Kanyakumari to Kashmir, it will run parallel. Nobody can enter the territory anywhere. You will have to keep on drawing. It will meet at infinity, you say in mathematics. So this property is called asymptotic property to the horizontal axis. Mathematicians unfortunately call it asymptotic. I have not called, but I go by them. But what it primarily means is I extend. So you have 6 sigma, 7 sigma, 14 sigma, 99.999, it will not touch. It will run. Even if you cry, no, nothing. As a child, if you cry, they will give you chocolate. Here, nothing. It keeps on. You cry or laugh, it will not tire. Then the normal distribution has 2 parameters, the mean and standard deviation, which will have to be specified to understand the normal distribution. For the sake of academics, since our friend asked, the density function fx is written as 1 upon sigma root 2 pi e raised to the power minus x minus b whole squared by 2 sigma squared minus infinity less than x less than infinity the domain, and all real numbers it is this. Now, if you look at the exponent, it is an elliptic function. Suppose I take different values for a specific mu and sigma. You take an example where mu is 20, sigma is 5, let's say, and keep on varying the axis and plot this fx, it will look like a bell. It will look like a bell, but the bell may be, if your standard deviation is very high, it may look like this bell, or I shrink the standard deviation, another bell may be there like this, but it will be a bell. Why? Because one side is the mirror image of the other, and this will go. In other words, even when you start drawing this, one side will keep on going like this, and then there is a plateau here, and then it goes like this. So that is the property. Hence it is called a bell. Now why I am using the word density function here? How do I, in other words, compute probability for a continuous distribution? Supposing I want probability x greater than 3, how will I find out? Normally, how do you find out? Integrate that. So the area of the curve for a continuous distribution is the integral value. You integrate and with the limits that are given there for you. That's called Riemann integral because it's the area of the curve. So area of the curve at a point is what? Suppose probability x is equal to 2. How will I find out? 0. Because area at a point will not exist. So integral 2 to 2 fx dx is 0. So in a continuous distribution, probability x greater than 2 is same as greater than or equal to 2. So it's the area of the curve. So the area of the curve I need to find out, I have to integrate this. Now mu is the parameter, sigma is another parameter. Both you have to specify. Then a problem, suppose x is measured in centimeters. I need a normal curve, area curve, I need a table, or Excel of course can do, software. Suppose x is in kilograms, I need another area, I have to find out. Suppose x is in dollar, currency, I need another table. So what statisticians have done, if you are writing an exam where they say computer is not allowed, only calculator and a textbook table they provide, then they say we can solve the problem by standardizing this. Z is equal to x minus mu by sigma. When I standardize this, I have a normal distribution with mean 0 and standard deviation 1, and make a substitution. Z is equal to x minus mu by sigma. This will become z squared by 2. Sigma is 1, root 2 pi, 1 upon root 2 pi e to the power z squared by 2. And with this I can solve because z is independent of the unit. The mean of the z is 0, standard deviation is 1. In other words, all problems I can convert. It is just a transformation of scale and origin. I am not doing anything else. In other words, I am expressing the normal distribution in z units. In the American style, z units you can say, or z units. This is one word which I always feel both are correct. Zebra you are saying, you don't say ZTV, ZTV, zebra, but zest word, Z pronunciation comes. So both Z and Z, whatever you want you can use. Now this e raised to the power minus z squared by 2, 1 upon root 2 pi makes me say the original normal distribution I am expressing in Z units. So that Z does not depend on the scale. I can straight away get the answer. The textbook tables, others are built around that. When you are writing a professional examination, they will not allow you to use the other ones. Is it clear to you? So, in that case, necessity is the mother of invention. In Tamil you say, Vallavanukku pullum ayudam. The meaning is, if you are a Vallavan, if you are an expert, even a grass can be a powerful weapon for you. Standardized normal distribution has mean 0, standard deviation 1. The classical books used to say it has mean 0 and standard deviation unity. They use the word. Unity means 1. Unity. You can check that. Google, you can Google and do that. Unity. Fisher has used unity, so we can use that. So mean 0, standard deviation 1. Everything is same. There is no change. Now, quality control, process analysis, mission capability, demand projections, vendor rating, everything revolves around the bell curve. Six Sigma, bell curve. Kaizen, bell curve. Deming cycle, bell curve. Plan, do, check, act. Everything requires this bell curve. And in fact, the world has been, and it is still somewhat intoxicated with bell curve. If it is not a bell curve, they are disturbed. You cannot do process capability, you cannot think of a Six Sigma standards unless you bring the system in a state of stability and control using the bell curve. So this is extremely important. But let's understand how the normal curve works. The morning breakfast cereal pack weighs 0.29 kg with a standard deviation of 0.025 kg. The random variable weight of the pack follows a normal distribution. What is the probability that the pack weighs less than 0.28 kg? What is the probability that the pack weighs more than 0.35 kg? What is the probability that the pack weighs between 0.26 and 0.34 kg? Let me answer the question first using Excel, then using R, and conclude the session. The first step you have to do in a normal curve is to plot the function. You just plot it. So I am not drawing it to scale, but I am just sketching it now. So the basic thing is the first part, if I take it, it is a bell curve here. This is 0.295. Am I correct? This is 0.295 is the mean of the normal distribution. Standard deviation sigma 0.025. That's all same for all. And you want the probability that the pack weighs less than 0.28. So intuition tells you 0.28 must be left of the mean. So let us say I put it somewhere here. 0.28. Therefore, this area is wanted. Am I correct? This area is wanted. What is this? We have answered the problem. Now, the second situation is more than 0.35. So let me just put here 0.35, more than this is wanted. I am not drawing to scale, but I am just explaining this to you. The third one situation is between 0.26 and 0.34. Let's say this is 0.260, this is 0.34. This area is wanted. This is what? If you answer, you have done the normal curve. Am I right? This is the basic idea. So the first step is understanding the problem, sketching the graph, very, very important. And if you do that, even if you make some mistakes, you can correct it because you have a very clear concept. You've got the diagrams in place. So let us answer this. In the Microsoft Excel, there are functions norm.dist, norm.inv, norm.s.dist, norm.s.inv. 4 functions are there. Depending upon the nature of the problem in the normal distribution, you are supposed to use them. So let me demonstrate that to you first. Excel's convention is, if I have any normal distribution, I need not convert it to Z. I can do it in Z also. It gives the cumulative probability X here. From the left to X it gives. X can be on the right or the left. In other words, it can equally do cumulative probability if X is here also from left to this. In other words, when it is left of the median, it is straightforward. Suppose I want the cumulative probability for this, I will have to subtract from 1 the cumulative up to this, because it is on the positive side. Of course, you can have a minus X here. One side is a mirror image of the other. You can do that, but this is Excel's convention. Now, I can do in Excel for the original distribution directly without having to convert. I will also show you standardized variable of Z. In other words, if I convert this into Z, how to use that I will show you, and directly also I will show you. So what you do here is insert function. You don't have to memorize. There is an icon here, fx. Everybody can see. So you insert that function. Insert function. Then in the category statistical you put here. Are you with me? In the category statistical you put. Is it clear? In statistical you just type n. You have here norm.dist is appearing to help you. Is it there? Now norm.dist you put OK. You get a dialog box. X ordinate. Now first diagram what I want. So the directly Excel will give me the cumulative here. Am I right? Because it is the left of that, and therefore what is that I want? 0.280. Mean of the normal distribution 0.295. Standard deviation 0.025. Am I right? Then cumulative. This question is a logical operator. Do you want a cumulative probability or a simple probability? In the case of the binomial and the Poisson, this has relevance. Here, the continuous distribution is always the area of the curve, so you are talking only cumulative probability. And therefore, the logical operator must be put as 1. If you put 0, try. What is that you are getting? 13 point? 13 point this. You know what it has given? It has given the value of the density function. X minus mu whole squared by 2 sigma squared e power 1 upon sigma root 2 pi. It has faithfully done. When student asked, I actually demonstrated it was 13.3, then he was convinced. If you write it as false also, that means it will give the value of the density fx, but we want the probability, so put 1. Put 1 is true. So you get here 27.425% of the packs will weigh less than 280 grams. Is it clear? So supposing I want to use the Z distribution, ladies and gentlemen, now Z is equal to x minus mu divided by sigma. Am I right? So this 0.28 will become 0.28 minus 0.295 by sigma 0.025. How much is it? Minus 0.6 is equal to minus 0.6. So the area less than 0.28 is minus 0.6 units of Z. So in Z less than minus 0.6. Area x less than 0.28 is same as area Z less than minus 0.6. Now norm.s.dist. So let's go to the next column here, next row, insert function. As before, statistical n, and you have this function norm.s.dist. Supposing I use that norm.s.dist. Z, what is Z? Minus 0.6. Cumulative S1. And you shamelessly get the same answer. So with this background, can you do the second one on your own in Excel? 0.35, more than 0.35. So let me ask you the question. Can you do the second problem, second part in Excel based on what we have done? Is the left of that, my dear friend. So that's why I am giving you right of that now. Let's see whether you do. Hello? Ladies and gentlemen, I draw your attention. Probability area, the pack weighs more than 0.35 we want. So more than 0.35 is the second graph which I have. So what is the probability? It is more than 0.35. If you have to do it, it is the right of that. There are two ways to do. One way is equal to 1 minus cumulative. Please do that. Is equal to 1 minus cumulative 0.35. Let us see whether everybody gets it. Can I say that I am 99% confident that you are 95% confident you can do the problem? Okay? Excel gives the cumulative probability up to an ordinate x, and x may be on the right or the left. When it is in the left, the cumulative is straightforward. When it is on the right, when I want more than x, I have to subtract 1 minus this.
But the x-axis here, is that absolute number, weight?
We are using the norm.dist of Excel. Excel takes the original distribution as it is. We can also use norm.s.dist, which I have demonstrated to you, by converting this into Z. If you convert this into Z, what will you get? 2.2. Now, let me tell you the advantage. The cumulative probability when Excel gives, two cases arise. The ordinate x may be on the right side of the mean or the left side. When it is left side, the answer is straightforward. When it is on the right side, I want more than x, it is 1 minus. But I can prove a corollary to you by the symmetry of normal. If I subtract the deviation 0.295 to 0.35, it is 0.055. That 0.055, if I subtract on the left hand side, I get actually 0.24. So if you are very particular, I have to use that. I can take the ordinate 0.24 on the left side as a symmetry and shamelessly get the answer which I have put there. Because I know you will ask this question, I wanted to forestall, still you have asked, I have put that shamelessly, you are getting 1.39. If you still want to use only left side, you can use it. The deviation is 0.055, symmetry 0.055, I subtract here, no big deal, kindergarten stuff, so you get the answer, left hand side. Is it clear? See, whenever you are asking question, let's have clarity. You place, excuse me, let me make it clear to you. This is, hello, ignore this. You don't follow this. This is for some special query that comes. Symmetry, from this side, this is same as 0.24 here. But all I want to say, cumulative probability on the right of the mean means 1 minus I should do. When I want more than 0.35, I am saying 1 minus up to 0.35. Logic. That's all I am saying. The last one, how do you do that? It will be 0.34 area minus 0.26 area. Yeah. So, and you can use Z also, you will get this. Now, let me show you in R. The cumulative probability P norm. There is no confusion. You can just substitute. So, I just show you here P norm. So, let me first clear this console. P norm. P norm. Okay, sir? Mean is equal to, what is mean? 0. First the ordinate I have to write. What is the ordinate? 0.28 is the same as left tail of Excel, same thing, 0.28. Then mean is 0.295, standard deviation 0.025. By default it takes the left tail in R. In R by default it takes the lower tail. You get the same answer shamelessly. The advantage is I don't have to say cumulative operator 1 like Excel. Excel I have to enter, R straight away accepts it. Mean is equal to this, standard deviation is equal to this. I can write it also The first one is the ordinate, second one is the mean. I can do like this also to be on an orthodox way, P norm of 0.280, comma, mean is equal to 0.295, comma, SD is equal to 0.025. Then also you'll get the same answer here. In other words, I want to be sure that I am entering mean and standard deviation. The order, supposing I have changed, I have a doubt. By mistake, I put standard deviation first, then I may get a wrong answer. So I put mean is equal to this standard deviation. It accepts that. What is the second one? Greater than. By default, R takes left tail, like the Excel. So 1 minus P norm this, you can do that. But the another way of R is, I put here P norm of 0.350, comma, mean is equal to 0.295, comma, SD is equal to 0.025, comma, lower dot tail is equal to false. Is equal to false. Kadak. Straight answer. Which pleases our friend. Directly you are getting. Lower dot tail is equal to false. I don't have to subtract. Excel we don't have the luxury. Here, because by default it takes lower dot tail, I get your point. See, the upper tail, it does it here in the R. Directly you will get. So the confusion is resolved. There you have to remember. See, why am I doing Excel and R? It's a simple thing. In the initial stages, let us not undermine Excel. Excel is still a force to reckon with, even in advanced analytics, big data and all that. There are so many functions and capabilities today in Excel which are mind-blowing. So let us not think it is inferior, it is superior also. And second, people who are comfortable with Excel also should have something initial stages of learning. So this is R. Is it clear? Similarly, the other one, what will you do? P norm is this. This is P norm 34260. 88.33% of the packs. Have you done that? The last one. Now a question comes. I will put a puzzle for you. Probability is equal to this. Put a bracket here. Talk 100. Now print probability digits is equal to 4, let's say 88.33. Digits is equal to 4. 88.33%. So you can get that. And some more formatting, floating constant and all available. You can do all kinds of stuff. It's possible. If you use the libraries, it's available. Digits and all that, and you can do that. But I prefer a decimal. Decimal is always convenient. Because in Excel also, when I make it percentage, by mistake, if I put another percentage, some stupid things come and then trouble you later. Play safe with a decimal. So last question before the closure is a puzzle to you. See whether you can solve. A puzzle is the same problem. The mean is 0.295. Standard deviation is 0.025. Everything is fine. Now, what weight of the pack was exceeded by 80% of all packs produced? What is the weight that 80% of the packs produced would have exceeded? You get the point? What is the weight? This is same 0.295. 80% of the packs would have exceeded. Let's say this is X. This area must be 0.8. That means 20% of the packs would have not have achieved this weight. So what is the weight of the pack that 80% of the packs would have exceeded? What weight 80% of all the packs produced would have exceeded? Ulta, inverse. So norm dot in function. Norm dot in is available in Excel. So when I say 80% of the packs would have got this weight, 20% would have got less weight. So you simply put here norm dot in function in Excel. Let's say here norm dot s dot in is later, I will tell you next time when I come. So norm dot in mean probability you want 0.2. I cannot put 0.8 cumulative. Less than weight. 80 would have exceeded, that means 20 would have got less, 0.2. Mean is how much? 0.295. Standard deviation? 0. So 273.96 grams or approximately 274 grams or 0.273 kg. 274 kg. 0.274 kg or 274 grams is the weight which 80% of the packs would have exceeded. 20% of the pack would have got less than 273 grams. Now how do you do it in R? Q norm, P norm, Q norm, ST, isn't it? OP, QR. So Q norm, Q norm. So put here Q norm. Either I can put 20 Q norm. The probability is 0.8, comma, mean is equal to 0.295, comma, SD is equal to 0.025, comma, lower dot tail is equal to false. Directly like a laddu you get the answer. But if you put 0.2 also you will get the same answer. But I don't have to do. Lower is false. Right, I get the answer. Let's stop here. I have done the bell curve basic concepts. How to do it in Excel and R. And descriptive part. And the concept of probability. In this residency we have covered within the allotted time. It has been a great pleasure interacting with you. Let's hope our paths would cross again in the next residency on the 24th and 25th. The remaining part we will do. Wish you the best. We'll meet. Thanks a lot. Thank you for the time.